Hello everyone. Welcome to Chapter 9, Electrons in Atoms. So in this chapter, we're going to focus primarily on where the electrons are in a particular atom. So electrons are really important to atoms. Electrons are how connections are made between two atoms to form either an ionic or covalent bond. So because those electrons are the ones that participate, that make bonds, that make connections between atoms, we need to take a little more closer look at being able to say where in the atom an electron is. So if you remember from previous chapters, when we talked about the model of the atom, we talked about primarily two different models with respect to differences in electrons. In the J.J. Thomson plum pudding or blueberry muffin model of the atom, those electrons were kind of just stuck, embedded in a positive charge that was in the atom. And in J.J. Thomson's model, those electrons were immobilized, stuck within that positive charge. Okay? So we moved from this blueberry muffin or plum pudding model in the early 1900s to a model from Ernest Rutherford just a few years later in 1911. The main difference between J.J. Thomson and Ernest Rutherford's model is what the electrons are doing. In J.J. Thomson's model, those electrons are stuck within the positive charge of the atom. But in the nuclear model of the atom, we have a dense core of protons and neutrons called the nucleus, and those electrons are just kind of hanging around outside of the nucleus. And the majority of the atom is empty space. Okay? So that's where we last left where electrons are in an atom. We basically said they're just hanging around outside of the nucleus where the positive charge is, and the remaining atom is empty space. So the model that we're going to talk about and investigate in a little more detail in this video is called the Bohr model, named after Niels Bohr. So you can see that a similarity between Rutherford's nuclear and the Bohr model is that both have a nucleus, a dense core of protons and neutrons. But in the Bohr model, those electrons are in very specific regions or paths that travel around the nucleus. So in this cartoon picture of the Bohr model, the electrons, which are the little red dots, are in specific elliptical paths that travel around the nucleus. Those electrons are not just placed any which way around the nucleus. Okay? So this Bohr model is something that we're going to talk about in a little more detail with this video. So in the Bohr model, those electrons, they travel around the nucleus, and those paths that the electrons travel in are called orbits. In this cartoon I have here on the right-hand side, those orbits are labeled in terms of particular n values. So I have n equals 1, n equals 2, n equals 3. Those are the orbits for this model of the atom. And as you get further away from the nucleus here is this positive charge in the center. As you get further away from the nucleus, the energy level, or the n associated with that orbit, increases. So that means that the further away you travel from the nucleus with respect to orbits, the greater the energy that orbit has, and that electron has when it's in that orbit. Okay. So again, looking at this cartoon on the right-hand side, you see that our orbits increase in values of whole integer numbers. So I have n equals 1. That's the closest orbit. As I get further away, I increase by values of 1. N equals 2, n equals 3, so on and so forth. The further away you get from the nucleus, the greater the n level, the greater the orbit number, and the greater the energy the electron has in that orbit. And so, excuse me, a few things that you can see aside from that orbits increase in whole integer values. You can also see that orbits, there's no 1.5 or 1.25 orbit. Okay, so that means that the energy is quantized. It has that energy of the electron in that orbit has a specific value. Kind of liken it to this concept of quantization. I kind of allude to it with this stair-step model with the ladder. Ladders have steps in even integers. There's no 1.5 step. Okay. As you increase or get further away from the nucleus, your n increases. So your energy level increases. That's the first point. Second point is that when you travel further away from the nucleus, your energy level increases, but you can see kind of in this cartoon on the left-hand side with the stair steps, in most ladders, stair steps are evenly placed. Are they evenly placed in this cartoon? They are not. So when traveling further away from the nucleus or up the ladder, you are having more energy, but the distance or the difference between energy levels is not the same. What that means is that if I had an electron at the n equals 1 orbit, the energy it takes to go to n equals 2 is different than the energy that it takes to go from n equals 5 to n equals 6. Okay? So, energy of orbits is quantized. It has specific values. The difference between energy values is not equal. The further away you get from the nucleus, the more energy you have, but the difference between energy levels decreases. Okay? So those are some tenets for the Bohr model. And the reason why Bohr's model was so important that it got him the Nobel Prize for it, is that it could correctly predict the energy level for an electron in a hydrogen atom. So if you look at your periodic table, you see that hydrogen has an atomic number of 1. That means it has 1 proton, which is positively charged, and a neutral atom of hydrogen is going to also have 1 electron, because if it's neutral, you have to have the same number of protons as electrons. So let's look at the Bohr model with respect to a hydrogen atom. That's the simplest atom that we chemists have because it only has 1 electron. So let's look at hydrogen with respect to the Bohr model. And here's a cartoon of hydrogen. We've got our nucleus here at the center. And let's say we have our 1 electron, and it's traveling in this n equals 1 orbit. It's the lowest energy orbit available. Let's say that that electron is excited, meaning we give that atom some energy. What the atom will do with that energy, specifically what the electron will do with that energy, is get excited. It will absorb that energy, and therefore that electron, depending on the amount of energy you give it, it will be promoted to a higher energy orbit. So in this example here, I have the electron being promoted to the n equals 2 orbit. Okay? So giving electrons energy It excites them and promotes them to higher orbits. And electrons, just like people, they don't want to have a lot of energy. They want to be at a ground state. They want to relax. And so eventually that electron, if it is at a higher energy orbit, will relax to a lower energy orbit. And when that relaxation happens, the release of that energy will be in the form of light. That light can either be visible, meaning in the rainbow spectrum of red, oranges, blues, or yellows, or it might be with a wavelength and frequency that we can't see. The point is that when electrons release their energy, they go down to a lower orbit, and that energy is released in the form of light. And so what's so exciting about this model, Bohr's model with respect to hydrogen, is that when you do calculations regarding energy and light with regards to the Bohr model for hydrogen, all the math works out, essentially. You talk a lot more about the math in Chem 1, and if you go on in chemistry to like physical chemistry, we're not going to talk about the math. You just need to know that this model, the Bohr model, works great when predicting where an electron is in a hydrogen atom. And remember, hydrogen only has one electron because it only has one proton. Well, that's great for hydrogen, but what about all those other elements on the periodic table that have more than one electron? That, unfortunately, is where the Bohr model fails. So even though we're going to use some of the same concepts with other atoms, we need to look for a different model to explain where an electron is in an atom that has more than one electron. Okay? So we need to have another model. And that next model, the other model, is going to be something that deals with something called quantum mechanics and Schrodinger's equation. Don't get scared about those terms. We're going to talk about them in more general terms in the next video.